Good morning, boys and girls. This is a short video about reservoir rock types. Now, it's a much, misused concept, I think, in carbonate petrophysics. The first thing to say about reservoir rock types is that they are not preordained like geological facies. They're not something which you discover that it sort of exists there in the rock, like a crevasse splay facies or something like a geologically made thing that you're sort of finding. It's not like that. Reservoir rock types are really simply a group of rocks that can be a group of different sorts of rocks that can be evaluated with one set of equations. Now, when I say evaluated, I mean the data that you have can be put through these equations and it can generate the required inputs for the geological model, such as porosity, which we normally have fairly simply, saturation, permeability, and free water level depth. And there are other derivatives like SOR, residual oil saturation, and relative permeability, etc. as well. So that's the idea. That you've got a group of rocks. You've got a group of rocks, and they can be. We've found by trial and error we have found that these group of rocks can be evaluated with this set of equations, and they always give about the right answer. If we take another type of rock and put it through this set of equations, we don't get the right answer. So therefore, I would call that other type of rock a different rock type, because it cannot be. It needs its own set of equations to get the answers, right? Normally, in a carbonate reservoir, you'd have, in my experience, 2 or 3 major reservoir rock types, and then the task of the petrophysicist is to generate the reservoir rock type equation set for each of the major reservoir rock types. Normally there's a dominant one, and then there's another one that's maybe 30% of the hydrocarbon pore volume or something, and you need to evaluate that one as well. And of course, you need the data to do that. Right. So, pardon me. So the data that we have typically to find these reservoir rock types is not just core data, right? If you only do it with core data, then you're kind of missing the point, because you're going to have a lot of exciting looking hard data results. But the point is that we, of course, don't have core everywhere, do we? That's why we log, right? We run logs because we can get logs all down the well track. And we get core basically because we want to calibrate those logs and see what those logs mean in terms of real reservoir properties. So we might derive the equations in the core data. We will probably, but they have to be found. Those different rock types have to be found by logs, and the equations have to be driven by logs in the end as well, right? So remember that it's not just a standalone core process. If it is, you as a petrophysicist need to actually kind of stop it, because these things can go off, and develop a life of their own. It turns into this crazy science project where you've got all these amazing things happening. But hang on a minute, what do we do with all this stuff? How can we actually apply it to the reservoir? We can only apply it to the reservoir if we can find the rock types with log data, and if we can drive the equations with log data. Right? That's okay. So the data we use is, of course, core data, porosity, permeability, cross plots, capillary pressure data, very important, mercury injection, capillary pressure, and pore throat size distribution data, thin sections to understand, to sort of get your mind into kind of understanding what this behavior is. You find thin sections they're not very quantitative, but they do help you to kind of understand what's going on. And then, of course, log data, image logs to find the rock types often. All the density neutron regular logs. NMR logs are often very important, and dielectric may or may not be important. But rock typing is a very interesting subject, and it is a function of not just core, but also the logs. The other thing, when you've sorted out your clusters of rocks that have similar relationships between the log data that you have and the answers that you need in the geological model, then you need to also, when you're calibrating your equations, which is, as I said, the primary task of the petrophysicist, is to create this bank of equations that do this job of taking the data to the answers. Then you need to really append to that rock type, or that equation set, the borehole type, the sort of borehole environment in which those were derived. For example, is it an 8.5-inch oil-based mud LWD type data set, or is it a water-based mud 12.25-inch hole conventional logging, wireline logging data set, because sometimes you'll find that the equation set is not really so good at doing it when you've changed the borehole environment dramatically. Okay, because of course logs are created in an environment which is the borehole and the mud, and if that changes dramatically, you might find that there's some. I mean, we try and get rid of those differences, right, with environmental corrections. That's what they mean, but they may not be perfect. So it's a good idea to append your reservoir rock types to the primary borehole type and logs and mud system that you use to derive it. Okay, so let's move on now to, I should have shown you my, oh, there we are. Okay, okay, this is the objective then is to a group of calibrated equations that transform the collection of data that happens to exist in a reservoir study into the most accurate petrophysical results possible for a rock type present in the reservoir. So it's always data, equation set, answers. Now, a reservoir rock type equation set is the medium through which all available data retains its most effective use in the geological model. And as I said, it's an ad hoc process because it's a function not only of the actual reservoir, the geology, it's also a function of the data set that you've got with that geology. So those two things mixed together, that's why it's sort of an ad hoc process. And also I want to point out that it may involve calibrated theoretical models. However, I don't agree with forcing preconceived pure theory like Cassini-Kármán into this process. You want to petrophysics is empirical, and you need to look and see what works and then use it. It may or may not fit in with some preconceived notion about Cassini-Kármán or flow zone indexes or whatever else you might come up with in a mathematical textbook. It's not only about maths; it's about what you observe to work. Okay, let's go on to the next slide. So reservoir rock types, why then? This is kind of summary slide of all this. Objective to identify a group of rocks that can be evaluated with one equation set. And I normally, because I often use the J function, I normally sort of define my rock types in terms of a J function. In other words, if that rock can be evaluated in this J function and get me the answers that are reasonably accurate, then I'll call it that rock type, right? If I find that it won't, if I find that when I pump it through that J function, I get really wrong answers, I say, oh, I can't really put that in the rock type. I've got to have another J function for that rock, right? So that's how I normally do it, because a J function does, of course, include three of the primary things that we need, right? It includes porosity, permeability, saturation, and height. So four of the things that we need are in that equation. That's why it's such a sort of powerful equation. Yes, the logs that we might use would be image logs, NMR, acoustic, dielectric, and of course apparent M in the water zone, because that's going to be, if you're using resistivity in your evaluation, M is going to be an important thing, isn't it, to worry about. You can't have rocks with different M values or different M trends with something else that you're looking at with the real reservoir saturation in the same rock type. You've got to split them out if you're going to use resistivity as a main part of your saturation determination. And the ratio of VUG porosity over porosity is also normally quite an important parameter to look at for your different rock types. The applications, of course, are to predict permeability, to predict saturation height, to predict free water level, if you know what those two are, relative permeability, residual saturation, etc. The things to watch out for as a petrophysicist who's sort of maybe overseeing all of this process is this reservoir rock type fails, I call them, are things like core-based reservoir rock types which cannot be found or used with logs. These are really useless because you can't do anything with them. They're nice, interesting science projects, but now what do? You've got to use logs. You've got to be able to apply all that understanding via the medium of logs. So they must be able to be found with logs and log-driven. The equations must be able to be log-driven. Wrong reservoir rock type identification beyond core, and focus on theory, not answers. Often you get, like I said, I haven't said in this video, but I've said before during lectures, I've been to a number of reservoir rock type presentations, and they've been quite, learned and interesting and very well done, but they haven't really understood what we're trying to do. We're trying to build a geological model from logs. The cores are help us with that process, but we are condemned in a way to using logs to do it, right? Because we don't have core everywhere, do we? So we do have logs everywhere, all down the well track, so we have to use logs. So they need to understand that we're going to have to apply all this learning through logs. So that's really all I have to say on reservoir rock typing, and that's all. Bye.